Okay, so this is the start of probability. These 2 pages here, I'd appreciate it if you read through these. I'm going to go through. I am not going to read them to you. This right here is formulas that you're going to keep for later. I know some of you turn the volume down. Excuse me. So I wrote that so you would see it. This is theoretical probability. And the basic idea, you guys, most of you do understand what theoretical probability, the probability of favorable outcomes over the total. So favorable over the total. So if we want to know, probability of getting a 2 on a die, that would be favorable. There's 1, 2 on a die, and the total would be 6. So that's the idea behind that. So we have all these. Please read these over before we get to the next section. Okay, so are the events mutually exclusive? So right here, I'm going to do the first 2, and then we're going to go over these in class. So a pair of dice is rolled, and one event is we have a sum of 4 and a double. So we want to know if these 2 are mutually exclusive. That means that if there is no overlap. So it might be easier to think about it. Are they exclusive? Okay, so if you think about it, rolling a sum of 4, can you get a roll of sum if you roll a double? Well, yes. If you roll a double, that's 2 plus 2. Okay, so there's overlap. So these are not mutually exclusive. Okay, anytime there's an overlap where the same thing can occur and satisfy each of the events. So each of the events will be true. If I roll a 3 and a 3, it's not a 4. The sum isn't 4, but there is a possibility of an overlap. A pair of dice is rolled. The sum is 7, the sum is 11. There's no way those could possibly overlap. I can't get a roll of 7 and a roll of 11 at the exact same time. So if you look up here, I can get a 4 and a double at the exact same time. So they are not mutually exclusive. They are not mutually exclusive. I just had a freak out. And then here, I can't get a 7 and an 11 at the exact same time. So these are mutually exclusive. So don't do 3, 4, or 5, but try the other 2. I think there's 3 down there. Okay, are these events independent or dependent? Well, independent and dependent, does one event change the other? So with these, there's always 2 events occurring, one following the other. With mutually exclusive, there isn't. It's whether events can happen at the same time. So with independent and dependent, there's 2 events, one happening first and one happening second. So here, if we look at this problem, a bag containing these things, we draw a chip looking for an even, and we replace it. And then we draw a chip looking for another even. Well, since this value was replaced, this one is not dependent on the other one. So these guys are independent. Okay, so look at it this way. If it's replaced, it's independent. Okay, if it's withheld or not replaced, so we draw a card from the deck and we hold it. When we hold on to it, it's changing the probability of the next event. So this changes the probability. Well, so when something gets changed, then it becomes a dependent event. So let's look at this one. We have a box, okay, 20, whatever, doesn't matter. I see it's not replaced, and then I pick another red marble. The probability has changed. So the probability of this one is 5 out of 25. And then the probability of this one would be 4 out of 24. So these 2 events, one happening after the other, this one is dependent on whether or not you get a red or you don't get a red on that one. So this is dependent also. So try the rest of these, and we'll go over them tomorrow. Over here, find the complement or the probability. So this is just definition-wise. A fair coin is tossed heads, so the probability of getting a heads is 1/2. The complement is the probability of not getting a heads. So we often think about that as 1 minus the probability, or in this case you could just think of not getting a head. So the probability there would also be 1/2. So a fair die is tossed. Roll a 4 or a 5. So the probability of rolling a 4 or a 5, if we roll a 4, the probability of that, so it's a die. So there's a 4 and a 5, there's 2 values there, so that's 2 out of 6. So the complement of this would be 1 minus this, or 4 out of 6. Okay, so complement is what's the probability of it not happening? Okay, a pair of dice, these guys, doing the sum is just a pain. It just takes too much effort. So don't do that one or this one, but try the rest of them, please. Okay, independent and dependent events, actually finding the probability, how that works. All right, so these 4 are either independent or dependent. When we look at these, you flip a coin, and then you roll a fair die. So these are 2 events occurring. The coin lands heads up, and the die shows an even number. So the word "and" generally says that you're going to be multiplying events together. So this is the counting principle. So the probability of rolling a head is 1/2. An even number is 3 over 6. So the probability of them together would be 3 over 12. So these 2 are independent events. If I flip a heads on this one, it does not affect if I roll an even number on that one. So these are independent events. I can simply just multiply these 2 things together with a clear conscience. Okay, so this one here, you roll a fair 6-sided die twice. So these are again independent because one occurring does not change the other. So the first shows a 5, so that's probability is 1 over 6, and the second shows a 6. That's also 1 out of 6. So the probability of those both happening, one after the other, is 36. Or is 1 over 36. There are 8 shirts in your closet. Yes, there are 4 blue, 4 green. You randomly select one to wear on Monday and a different one on Tuesday. You wear a blue shirt for both days. Now, this is assuming we don't do laundry and we're not going to wear the same blue shirt, okay? We're just going to deal with that. So it's 4 out of 8 times 3 out of 7. So you can see I took the blue, I wore a blue, so now this is day 1. On day 2, I no longer have 4 blue, I only have 3 blue. So these are now these are now dependent events. This event depends on this one, so I have to change the probability. Still multiply them together, but I get 12 out of 56. So here, same difference. You have 5 apples and 7 peaches, that is 12 total. So what's the probability? You take one piece and I eat it. So when I take the piece and eat it, what's the probability that the first piece is an apple? So I eat the apple. I picked an apple out. Now I want the probability that the second one is a peach. Well, I didn't eat a peach. So even though I have only 4 apples left because I ate one, I still have 7 peaches. But my total, I only have 11 left. So that's how that one changes the probability here. Okay, so these are also dependent events. Even though it wasn't an apple also, I did eat one of them, so the total does get changed. Mutually exclusive. Now generally with mutual exclusive, it's one event. Okay, one event occurring in different ways, and they could both happen at the same time. That would make them not mutually exclusive. So a magazine contains 14 pages. You open to a random page. The page number is 3 or 7. So the only possibility of that happening, there's only 2 of them. There's a 3 and a 7. 3 and 7 cannot happen at the same time. You can reduce them if you want, but at this point we're just trying to muddle through. A bag contains 3 apples and 3 peaches and 4 pears. You randomly select a piece of fruit. It's an apple or a peach. Now both can happen at the same time, so these guys are mutually exclusive. So I just can count them up. An apple or a peach, we got 7, and the total of them, there are 10 total. So apple or peach, I simply or generally, well, or means we add things together, and we can just straightforward add because they're mutually exclusive. When they are not mutually exclusive, we have to take that into account. So for example, you have a fair die. Oh, really? That's exactly what happened. 1, 2, 3, 4, 5. We have a fair-sided die. The probability, the die shows an even number or a number greater than 3. So an even number is 2, 4, and 6. A number greater than 3, 4, 5. Well, we can circle them. You can do whatever you want. But you can see there's overlap. The 4 and the 6 are overlapped. We can't count them twice. So the total possibility is there's 1, 2, 3, 4. I can't just straight add them together. I have to make sure I don't count these 2 values twice. So that's when these guys are not mutually exclusive. You have to subtract the overlap or not count the overlap to begin with, meaning you can have an even number greater than 3 at the same time. Okay, box contains red playing cards. Okay, the box also contains a black. All right, so we have red, 1, 2, 3, and black, 1, 2, 3, 4, 5. When we have this, it is black or has an odd number. So black is all of these. Has an odd number would be this one, this one. Okay, so these 3 are overlapped. I just have to make sure I don't count them twice. So there's 5 of them here, and there's 2 of them here. So we simply add those together, and it's 7 out of 8. This is the only one that doesn't get circled. Now we have conditional probability. With conditional probability, it's the fact that something has been given already. You know that something is true. This is the formula here. Okay, and we're going to use that down here. A box contains black chips and white chips, etc. We want to know the first chip drawn. The probability is 3 out of 8. Find the probability of selecting a white chip on the second draw, given that the first chip was a black. So the first chip was black, the probability is that. We know that the total probability was 15 out of 56. So what's this probability? Well, you just figure it out. 3 times what? Excuse me. Here we are. Ooh. Sorry, I know it's a long video. 3 times what is 15? Well, it's 3 times 5. And 8 times what is 56? Well, that'd be 7. So the probability that the first chip to select, that the second chip is a white is 5 out of 7. Okay, so we can fill out this chart. Take a second and fill out this chart. I will come back with it filled. Okay, so hopefully you understand. These are male and female. We want to know yes and no if they think that women should be combated in the army, should be in the army, in combat. So male said 32, 32 said yes, 18 said no, so that's a total of 50. A total of 50 there. So 50 and 50, male and female. 40 said yes, 60 said no, and the total this way adds to 100 and this way adds to 100. The respondent answered, so we want to find the probability here that the respondent answered yes, given that it was a female. So we only want to deal with the females. So what it means up at the top here, this formula up here, this is the intersection over the given. So we're changing it. It's not over the totals anymore. It's over what's given. So we basically already know that this person is female. So I don't even have to count the males. So it's only out of 50 females. The respondent was answered yes. Well, there's only 8 females that said yes. So that probability would be 8 out of 50 instead of doing it out of 100 because we already know they were a female. The respondent was a male given that they answered no. So I only know that the person answered no. So right now, this is the given. So 60 people answered no. So that they were male, there's 18 males that answered no, so 18 out of 60. So that's what it means when it says given. We already know that's true. All right, have fun.